Lab 2, motion of a falling object. Observe the motion of an object dropped from rest that falls somewhat slowly straight down. Used a ping pong ball, tracker video analysis, and Python computational models. We use Newton's second law to create the Python model. For a falling object, the net force is equal to the gravitational force downward and the drag force opposite to the motion. Newton's second law, velocity is equal to the old velocity plus F net divided by mass times delta t. From that new velocity, the position is updated. Since delta t is small, this is repeated with each v2 and r2 becoming the v1 and r1 in the next iteration. The model builds a predicted motion one small step at a time for physics. 3 computational models are shown in this lab. Free fall with only Fg and no drag force. Model 1 from the lecture, drag force is proportional to the object's velocity. Model 2 assigned in the lab, the drag force is proportional to the square of the object's velocity. Fd is opposite to the direction of velocity, hence the minus sign in the constants b and c, which are determined from the observed data. Initializing your Python model, the ping pong ball mass is 2.7 grams or 0.002 kilograms. The ball starts from rest with the 0 position and velocity at t is equal to 0. Other initializations are delta t is 0.001 seconds, g is 9.8 newtons per kilograms or meters per second, j hat, the y component unit vector, and b and c, b was 0.0013 and c was 0.0045 in my modeling to get it to fit the observed motion. Use 2 vector functions from Python, norm, ball velocity, and mag, ball velocity, to return the unit vector and the magnitude of a vector. The calculation loop is shown here. I have both models in the loop. One is turned off with the hashtags, the other one is on. Here is a screenshot of the tracker taking the data of the falling ping pong ball. You see the graphs and the data. Here is the position time graph of the falling ping pong ball, which was imported into the spreadsheet and combined with the data in the CSV files from the various runs of the Python model. Here you see the falling ping pong ball observed with gravity only, what would be called traditional free fall, no drag, and you see that the model underpredicts the or overpredicts the position of the balls. It does not match up. Here you see a run of the Python code with the weight vector shown and the building drag vector and the velocity time graph from the Python, and repeated runs of this were used to adjust it so that the final position of the ball was equal to the final position of the observed motion. Once that was done and the constant set, this is the falling ping pong ball observed versus modeled for the model assigned in the lab with the drag force proportional to the square of the velocity. The match is very good for all the points, a little bit of a wiggle down at the N2, but that may be observational. It looks like error because the ball becomes quite blurred. Here you have all 3 models, and it looks like the 2 models of drag, v proportional to v squared and proportional to v, overlap the observed data in the same way, giving a good match. What does it mean? Examine the VT graph predicted by your models. There is the VT graph showing free fall in blue and the modeled velocity using the proportional to v squared model to model the falling object. Here you see I extended the time of fall from the 0.6 seconds actually observed to about 2 seconds, and you see the velocity levels out. This is terminal velocity of 7.5 meters per second. What if you throw the ball down? The object has a terminal velocity when the net force is 0. That means the drag force is opposite to the gravity and add to 0, and this happens at a specific velocity, so this should not affect whether the initial conditions are 0 or some velocity. And when I do that, adding a downward velocity to my model, that is exactly what I observe. And that is the end of Lab 2. Thank you very much.